Okay, so section 3 was pretty much all about chemical reactions. Okay, so make sure you guys are able to know what a chemical reaction is. Okay, types of chemical reactions. So we have a few. Just going through these, actually we'll talk about those in a bit. Okay, so chemical reactions, make sure you guys just know what a chemical reaction is. What are some pieces of evidence that a chemical change has occurred? And know how to calculate the masses of substances. Okay, so right off the top, so what is a chemical reaction? So chemical reaction involves the formation of new substances. Okay, and what in particular are involved in chemical reactions? Is it the protons? Is it the neutrons? Or is it the electrons? The electrons. Wonderful. Okay. And if we wanted to get really specific, it is our valence electrons that are involved. Okay. So valence electrons involved here. Okay, good. And then we need to know some pieces of evidence that a chemical change has occurred. Can anybody think of one? What happens when you mix baking soda and vinegar? An explosion almost, yeah. It's like a miniature explosion, right? But bubbles are going to be released during that process, okay? So bubbles are formed, or a gas. So bubbles slash a gas is formed. What else? We had two main types of reactions. We had exothermic reactions and we had endothermic reactions, okay? So heat is produced. Was that endothermic or exothermic? If heat is produced, it's releasing heat. Exothermic, good. And remember, it's releasing it, so it's exothermic. You leave a building through the exit. Okay, that's how I remember that. So heat is produced, therefore exothermic. And what would an endothermic reaction be?
It is absorbed.
Yeah, perfect. Heat is absorbed. Absorbed or consumed in the process, right? Can anybody think of an example of an exothermic reaction? Yeah, so burning hydrocarbon combustion would be a really good example of that. Good. And hydrocarbon combustion would be an example of that. Very good. That's how we warm our homes. That's how I get to school in the morning. Okay. What would be an example of an endothermic reaction?
Those like ice pack things.
Yep, ice pack would be a good example for sure. Ice pack. Photosynthesis is another one. Good. Okay. We have some more pieces of evidence. So we have a gas being formed. We have heat being consumed or produced. We could have a precipitate. A precipitate can form. So if you're like adding two things together and then something like kind of settles out into the bottom, that's what a precipitate is. It like precipitates to the bottom, just like rain, right? They call it precipitation because water is coming down, right? So a precipitate is formed. Changing color. Yeah, so two more. So we have change in color, and or an odor can be produced. Okay, so make sure you guys are able to recall at least 3 pieces of evidence that a chemical change has occurred. Okay, you need 3. Next, you guys are going to need to identify the types of chemical reactions. So we have 5 main types. We have formation, decomposition, single replacement, double replacement, and hydrocarbon combustion. Okay, so we have 4 of the 5 up here. So what is this first one?
Formation.
This is a formation reaction, good. Because we have 2 elements coming together to form a compound, right? Good. What is this one? Decomposition. And again, we have a compound which is dissociating into its elements, right? What is this third one here?
Single replacement.
Perfect, single replacement. And you can tell that because we have a lone dance partner on the side, right? And then he's swapping out with A there, okay? So that's a single replacement. And then this guy here, the last one,
Double replacement.
is a double replacement. Good. And in that analogy, our compounds are tired of dancing with one another, so they swap cations, right? Perfect. And what did I leave out?
Carbon combustion.
Hydrocarbon combustion. Good. So hydrocarbon combustion can be anything. So CX, HX. Okay. It doesn't matter what numbers are on our hydrocarbons. Okay. This is just saying we have a hydrocarbon present. Okay. And that is just what a hydrocarbon is. It only contains carbon and hydrogen. Okay? So this is a hydrocarbon. What are we doing to our hydrocarbon combustion in a hydrocarbon combustion reaction?
Adding oxygen.
Yeah, we're burning it, right? It's a hydrocarbon combustion. We're burning our hydrocarbon. So anytime we are burning something, we're exposing it to oxygen. Okay? So anytime we're burning, we go plus O2. And what are my products always going to be for a hydrocarbon combustion?
CO2 and H2O.
Yeah, perfect. Carbon dioxide and water. Absolutely. Good. So make sure you guys are able to identify those tomorrow. Okay? Okay. Balancing and predicting chemical reactions. I still haven't decided if I'm going to leave that up for tomorrow. I don't know. We'll see how I sleep tonight. But you guys are going to need to know how to do this, okay? And I would not expect that to be on there tomorrow, okay? You just need to know this, okay? So, what is the first thing that we must do when we are balancing or when we're predicting reactions? What's our first step?
Identify the cations.
Absolutely. Okay, identify the anions and the cations. So Na is sodium. It's a group 1 metal, meaning it always has a charge of
Plus one.
+1. PO4, phosphate, is a polyatomic ion, which means we'll find it in the polyatomic ion table. PO4 is up at the top. It is phosphate. It has a charge of -3. Silver or sulfate? Which one is my cation? Silver, okay, it's a metal. Okay, so metals are generally cations. And I see silver is right here. It has a charge of +1. Sulfate is a polyatomic ion as well. And it has a charge of -2. Which makes sense, right? These are both, what? Molecular or ionic compounds? Ionic, okay? Metal, non-metal, metal, non-metal. So they should have a net charge of 0, right? They should have a net charge, and that's exactly what we have. So that's good. Okay, so now that we have identified our anions and our cations, those are going to swap. They're going to switch dance partners. Okay, so those will swap. So going out, so sodium and silver are going to swap places. So I'm going to have sodium sulfate. Okay, the charge on sodium is +1 and the charge on sulfate is -2. So we will need 2 sodiums. So it has a net charge of 0. So I'm just going to put a little 2 there because that belongs to the sodium. And now our silver and our phosphate are going to come together. So silver, phosphate. Silver has a charge of +1 and phosphate has a charge of -3, meaning we need 3 silvers. So that has a net charge of 0. Okay, so we have predicted our products, but are they balanced? No, they aren't. So let's do an in and out table here. Okay, and we'll just go left to right, writing down what is currently present in this reaction. Okay, so I have sodium first. Phosphate is present on both sides, so I will treat it as one thing. And then I have silver. And we have sulfate, which is also present on both sides. So we will treat it as one thing. Okay, going in, we have 3 sodiums. We have 1 phosphate, 2 silvers, and 1 sulfate. Going in, coming out, we have 2 sodiums. We have 1 sulfate, 3 silvers, and 1 phosphate. So, do I need to balance my phosphates? Phosphates are happy, same with sulfates. So we need to fix our sodiums and our silvers, okay? Again, we have a 3 and a 2, and a 2 and a 3. So the lowest common multiple of 2 and 3 is 6, right? So we need to get these numbers to get to 6. Okay, so how will I get 3 to 6? Well, if I just multiply it by 2, right? So I'll throw a 2 up here. Now I'll fix my in and out chart. So now I have 6 sodiums going in. I have 2 phosphates. Okay, so let's go and jump over here and we'll throw our 3 up on this one because we're still trying to get to our 6, right? So now we have 6 sodiums and now we have 3 sulfates, right? 1, 2, 3. And what do I need to fix now? We need to get our silvers to 6. So I'm going to put a 3 up here. Now I have 2, 4, 6 silvers, but I also have 3 sulfates. Okay, don't forget to fix that second one as well. Okay, are we balanced? No, we're close though, right? We just need to fix our silver and our phosphates. And we need to get 3 more silvers and 1 more phosphate, which is perfect. Because that's, we have a 3 and a 1. So I'll put a 2 up there. Now I have 2 phosphates and 6 silvers. Good? Okay. So again, make sure you guys are able to do this. So we'll just write our steps here. So step 1, identify cations slash our anions. 2, swap the cations. Identify cations, and don't forget, find charges. Swap the cations. Make sure new compound. Oops, that's a curly D. Make sure new compound has net charge of what?
0.
Of 0, good. Swap the cations. And then step 3, balance. Yeah, balance. Okay. I will be posting this video to the Google Classroom, so if you guys want to watch it again tonight, that would probably be a really good idea. Okay. All good? Okay, solubility of compounds will be on there. So get out your solubility table, if you don't have it out already. Okay. So, lead 2 sulfate. What do the Roman numerals indicate? Charge of the, yeah, perfect. So the Roman numerals indicate the charge on the cation. Good. So lead 2 means we have lead plus 2. And sulfate is a polyatomic ion, SO4 minus 2. Okay? So that is lead 2 sulfate. Now, you need to get your periodic or your solubility table, and in the top column is your ions. So you can either look for the lead plus 2 ion or the sulfate ion. I see the sulfate ion. Okay, point to the sulfate ion when you have found it. Okay, perfect. So let's go down that column and we'll see that most things are soluble. So as long as it's not in the low solubility category, it will be soluble. Okay? But now we need to go through the low solubility list. We have silver plus, well, the silver, and then I see the second one down is the lead plus 2. Okay? So this will be, it has low solubility, so we will say that this is a solid because it will precipitate. Okay. Potassium nitrate. Potassium is a group 1 metal, so it always has a charge of plus 1. Nitrate is a polyatomic ion. Okay, this is not potassium nitride. Okay, this is potassium nitrate. So nitrate is NO3. Well, sorry, I should have fixed that. Potassium looks like K plus, and nitrate is NO3 minus. Okay, so same thing. We can either look for the potassium ion or the nitrate ion. Okay, so point at the nitrate ion when you have found it, please. Perfect. So now we're going to go down that list. And we see that all ions with the nitrate has a high solubility. So we will say that this one is aqueous. And that means it is soluble. Okay. All right. Make sure you guys know how to do this. Actually, make sure you guys know how to do everything that I'm talking about today. Okay. Calculating molar mass. We did this yesterday, so it should be pretty fresh for us. So, if we are calculating the mass of elemental phosphorus, P4. So I know that the molar mass of one atom of phosphorus is 30.97 grams per mole. But how many phosphorus do we have? 4. Okay, so we need to multiply that by 4. So big M, remember, is molar mass, right? So molar mass of phosphorus is equal to what? Equal to 123.88. What are my units going to be on that? For molar mass. It's not a trick question. Grams per mole. Good. Good. Okay, calcium phosphate. So, calcium is group 1 or group 2? Metal. Group 2? Yeah, absolutely. It's right here, which means that it has a charge of +2. Okay. Phosphate is a polyatomic ion. So we could say, so calcium is +2. Phosphate has a charge of -3. And that looks like PO4 -3. What type of compound is calcium phosphate? Ionic. So it needs to have a net charge of 0. Okay? Again, here we have our 2 and our 3 situation. So lowest common multiple is 6. Right? So how are we going to get our +2 to 6? Well, we need 3 of them. And how are we going to get our -3 to 6? We need 2 of them. Yep. So I'm going to write that in a bracket. PO4, 2. Because we want 2 of the polyatomic ions, right? Okay. So molar mass of this. So calcium, and there's 3 of them. So calcium has a molar mass of 40.08 grams per mole times 3. And then PO4, 2. So there are a couple ways that you guys can do this. You can first find just the molar mass of the phosphate and then multiply it by 2. Or you could find, you could do P2 and O8, right, to find the molar mass of that, because currently we have, so 2 of the phosphate molecules, right, which means we have 1, 2 phosphorus, and we have 4 plus 4 is 8 oxygens in total there. Okay, so there's a couple ways you can do that. I'll do it how we've been doing. So phosphorus is going to be, where is it? 30.97 grams per mole times 2. I know there's 2 present there. And then we're going to add 8 oxygens to that. So I know oxygen has a molar mass of 16 grams per mole times 8, right? Because we have 4, 8, 2 phosphorus, and we have 3 calciums. Okay, so I did this example in particular because I want you guys to be careful with your brackets and the polyatomic ions, okay? So let's just put these in your calculator. So 40.08 times 3 plus 30.97 times 2. And I'm doing all that in the brackets just like we see up here, okay? Brackets are our friend. And then 16 times 8. So I get a molar mass of calcium phosphate equal to 310.18 grams per mole. Okay, any questions there? All good? Okay. Moving on. So finding moles from mass. So our formula from yesterday, N is equal to little m over big M. Okay, so I'm going to write that up here. What is N?
Number of moles.
Moles. Little m,
Mass.
mass of what?
The compound or
Yeah, mass of the sample, right? Mass of the compound. Mass of sample. And big M is molar mass. So aluminum hydroxide. So aluminum has a charge of +3. And hydroxide is OH, always has a charge of -1. Okay, that's a polyatomic ion. That's where it would have been. Got it? Okay, so what type of compound is aluminum hydroxide? It's an ionic, yeah, it's also a base, right? Because we have that hydroxide there. Okay? But yeah, so in this case, we want to have, we're going to need 3 of those. So that's going to look like AlOH3. Okay, so finding the molar mass of that. So aluminum has a molar mass of 26.98 grams per mole. We have 3 oxygens and we also have 3 hydrogens. So oxygen has a molar mass of 16 grams per mole times 3 plus the molar mass of hydrogen is 1.01 grams per mole times 3. So big M of AlOH3 is equal to what? Is equal to 78.01 grams per mole. So that is my big M. My little m is right here. Okay, so little m is equal to 10 grams. So we'll, now that we have little m and big M, we can just put this into our formula, right? So N is equal to little m, so 10 grams divided by 78.01 grams per mole. And we have 2 digits here, so I'll put it in 2 digits. So 0.13 mole. Okay. Again, when we're calculating the molar mass, just be careful of like the polyatomic ions when we have those like brackets on there, okay? Okay. Okay, so now we're getting into calculating Q. So we have a mass of water which is heated from 50 degrees Celsius to 98 degrees Celsius. Is there a phase change here? No. No, right? Because what temperature does water boil at? 100 degrees Celsius, right? So there's no phase change here. So which formula are we going to use?
Q equals MC delta T.
Perfect, okay? And if there was a phase change, it's right behind Harrian's head, we would use our heat of fusion or heat of vaporization formula, okay? So when there's no phase change, just a temperature change, we use Q is equal to MC delta T. Okay, so our mass is right here, so we have mass is 10 grams. We know, so C of water, this is on your guys' formula sheet, okay? I know it's 4.19 joules per gram degree Celsius. And my change in temperature, we can find that by, so temperature final minus temperature initial. So the final temperature is 98 degrees Celsius minus our initial temperature of 50 degrees Celsius. So delta T is equal to 48 degrees Celsius. So now that I know my mass, I know my specific heat capacity of water, and I know my change in temperature, we can just plug this into our formula. Okay, now in this formula, if you do not, or like in any formula in general, if you do not see a plus sign, you're assuming you're going to be multiplying it, okay? If there's no plus sign, just assume you're multiplying, okay? So these three values, we're just gonna multiply those together and find our Q value. So Q is equal to 2011.2 joules. Okay, when we do that, our grams cancel and our degrees Celsius also cancel, so we'll be left with joules. Yeah, and I'm fine if you leave it like this. If you wanted to give the best answer, you would give this in 2 digits, okay? But that's like physics stuff. Okay, so again, we're going to use Q is equal to MC delta T when there is no phase change, just a temperature change. Okay, one more example, and then the rest is your guys this time. Okay, so we have ice at its melting point, and it is melting. So, what formula am I going to use? Am I going to use Q is equal to MC delta T? No, good. Because we have a phase change here, right? Okay, so it's melting, so it's going from a solid to a liquid. So think of the ice like fusing into the shape of the cup, right? The ice is fusing into the shape of a cup. So we're going to use our heat of fusion formula. So Q is equal to N times heat of fusion. Okay, so that's our formula. And here is our mass, which is just a mass, right? 15 grams. What do I need to do to that so I can use this formula?
Find N.
Perfect.
Find N.
Yeah, so we need to find the amount of moles, right? Because this is in mass, in grams, right? So again, our formula to find moles, N is equal to little m over big M. So molar mass of H2O. So we have 2 hydrogens. Hydrogen has a molar mass of 1.01 grams. Times 2. That was my hydrogen there, sorry. And my oxygen here is just 16 grams per mole. And there's only one of them. So molar mass of water is 18.02 grams per mole. I hope that number looks a little familiar to you guys, right? The molar mass of water will always be 18.02 grams per mole. Okay? So to find number of moles, we do little m over big M. So our mass of the sample is 15 grams divided by 18.02 grams per mole. And that equals 0.832 moles. I would have included all those decimal places because this is an intermediate number. Never round your intermediate numbers, okay? Because it's going to affect your final answer, okay? So you can either like store that into your calculator or just leave it as here, right? So now that we know our N and we know our heat of fusion of ice, we can calculate our Q. So Q is equal to 0.832 moles. Now I haven't rounded that. I still have my full digit in my calculator. Okay? You guys, say it with me. We will not round our intermediates. Okay? All together. We will not round our intermediates. Okay? Good. Good, good, good.
Cool.
So yeah, you can just leave it in your calculator, but we're not going to round our intermediates. So we're going to multiply that by the heat of fusion of ice, 6.01 kilojoules per mole. So if I multiply that, I get a number. So we have 2 digits there, so I'll just leave mine to 2 digits. 5.0. What are my units going to be on that? Kilojoules, right? Because our moles and moles will cancel. So we have 5.0 kilojoules. All right.